welcome to another one of these ADD videos. Today we're going to be looking at the concept of related rates. This is where calculus gets a little intertwined with philosophy for a second. Why would I say that? It's basically because of the fact that everything changes with respect to time. That's actually the one constant in life, is that everything does indeed change with respect to time. What does that have to do with calculus, you might ask? Well, what is a rate of change but a derivative? And what do we derive? Well, we derive with respect to time. So if you think about this as my highlighter is a little too big, one second. If you think about this as a problem of implicit derivatives, the hardest part then just becomes setting up the equation. Once you set up the equation and you derive by whatever variable you derive, multiply by d whatever dt, where you can insert your variable of choice right here in the box, okay? And that would be deriving it implicitly with respect to time. So what are some related rates? Well, let's say this plane is flying overhead at, it's flying overhead in a horizontal line, and we want to know the rate of the angle change that this little observer is experiencing, so that would be d theta dt. And since it's flying horizontally, we have formed a right triangle. Say you know the speed of the plane. That would be the change in distance with respect to time. Miles per hour is a related rate. Okay, and let's say it's flying at a fixed distance of 5 miles. So that's a constant. Then you could use what piece of information, depending on how far the plane's traveled from being directly over her. Let's make it 5 miles as well. Then you could use a trigonometric formula. In this case, it would be tangent theta to look at your related rate, because it's going to have the horizontal distance, or the opposite leg, over that height. And since the height's constant, try to plug in your constants right away, okay? Only the things that change need to remain variables. So tan theta would equal x over the 5 miles that I'm referring to here is this 5 miles there, because it's flying at a horizontal distance. It doesn't go up or down. So that's a constant. And then if you wanted, you could multiply it over here. Then we would derive with respect to time, so forth and so on. Another example. Whoa, let's zoom out a little bit. That's a huge balloon. Let's say the balloon is being filled at a rate of half an inch cubed per minute. Or actually, let's say per second. It's a balloon, right? So in this scenario, what we have is basically a rate of change for volume. And assuming this is roughly a spherical shell, we could say the volume of the sphere is 4/3 pi r cubed, and then derive something like this. For example, let me just do one real quick. This would be dv dt equals, you bring the 3 down and multiply, which would cancel with the 3 in the denominator, leaving the 4 pi r squared. And since we derived the r, right, because we subtracted 1 from the exponent and brought it down, that ends up giving you a dr dt. So then you would need a radius. Let's say I wanted it at a radius of 10 inches. you would plug in that 10 for the R, and this would be your dV/dt. Try to keep an eye on the units. The units will help you determine that this is a volume because it's in inches cubed. If it was inches squared, it would be area. And then any distance like length, width, height, radius, those all would be in inches or feet. But the point would be this, the exponent would be to the first power. Now, if you see a d something dt, or if they say it's a rate of change, or in the units you see per some unit of time, notice set it equal to dV/dt, not to v. Okay, v would not have the seconds in the denominator. All right, let's look at this problem. I'm painting my house and I fall, and as I'm falling, I decide to make a math problem out of it so I don't think about the pain that's about to happen. And let's say I can approximate my rate of descent at 2 feet per second. It's pretty fast. And I want to know the rate at which the ladder is moving away from the wall. So in this case, that would be dx dt. And let's say I want to know it at a fixed height. So let me change to blue here. This is a different problem. So let's say this altitude that I start making the problem up is at y equals, let's say 10 feet. And then let's say that the ladder's 25 feet. Well, what equation can you think of that gives you the legs of a right triangle? Because this is a building, right? Hopefully this is a right angle, otherwise it probably has a bad foundation. Well, that would be the Pythagorean theorem. Sorry, I got a little distracted by my puppies. So the Pythagorean theorem would be x squared plus y squared equals z squared. That would be your main equation. And hopefully this ladder, as I'm falling down, is not banging me into the wall, right? Because it's getting shorter than longer. Hopefully this ladder is a fixed ladder. So I can plug in the constant right away. So then derive it with respect to time. And then that's the hardest part. Then just plug and chug what you know, all right? Try to make sure that you see stuff like this is a negative 2 feet per second because the height is diminishing. It's going down. So when you plug in this dy dt here, make sure you plug it in as a negative 2 feet per second, all right? So make sure you check out the example videos for related rates. And of course, as always, practice, practice, practice. Thank you for watching, and I hope I've cleared up any confusion you might have. Have a nice day.